Warning, the 50,000-degree wall protecting our solar system. The counters jumped before anyone spoke. Energetic particles fell off a cliff, cosmic rays surged, and a thin hiss in Voyager 1's headphones rose like a siren. "Something out there is hotter than any star's breath we expected here," I said, staring at a spike that shouldn't be possible so far from any sun. A 50,000-degree wall, too hot to make sense, too thin to burn metal, pressed against the edge of our solar wind. If it protects us, what's it keeping out? What is this boundary? How does it shield life? Where does it leak? And who holds the thermostat? Us, the sun, or the galaxy? The threshold, when the counters spiked. Voyager 1 was running on borrowed time. Power was rationed like air in a damaged sub. Heaters starved, instruments rotated, every watt argued over. Everyone knew there was one more crossing left in the old machine. Get it wrong, and we'd misread our own front door. The first hints came as nuisances, numbers that didn't settle. The charged particles we'd tracked for decades began behaving like nervous animals. Sudden drops in solar-borne ions, stepwise rises in the most penetrating cosmic rays. Then the magnetic field nudged right, then left, rotating in a way that made the room go quiet. That field line was supposed to be our map. Instead, it was a riddle. On a Tuesday that felt like a held breath, a solar storm launched months earlier finally reached the outskirts. Voyager's plasma wave instrument, two long antennas wired to hear the universe, picked up a tone. It wasn't music, but it had pitch. The frequency crept higher, a sure sign the electrons out there were packed closer than in the heliosphere we knew. That hum was the giveaway. The medium had changed. We were pressing on something denser. Meanwhile, far from the frontier, a small spacecraft orbiting Earth had been painting the sky with a new kind of light. IBEX turned invisible atoms into a globe-spanning image, revealing a bright ribbon arcing across the sky, an energetic neutral atom signal no one predicted. Cassini, orbiting Saturn, saw hints of the same thing with Inca. From two vantage points, the maps whispered the same sentence: there's structure out there. Inside the Voyager team, the debate wasn't polite. One camp saw the cosmic ray jump and said, "Outside." Another pointed at the magnetic field's orientation, which stubbornly refused to flip as cleanly as models expected, and said, "Not yet." The wall wasn't an official term, but it crept into hallway talk because nothing else fit how abrupt it felt. Here's the human side. An engineer who'd kept the spacecraft alive through 3 solar cycles rubbed his eyes and muttered, "If this is the end, it's a good end." A plasma physicist leaned over a printout and tapped the rising tone with a pen. "Listen to the density," she said. "The electrons are telling you where you are." In that moment, the sound mattered more than the picture. Stakes weren't abstract. If we mislabel the line, we misunderstand the shield that shapes every dose meter on the ISS, every silicon error in a satellite, every plan to send humans into deep space. The counters weren't just counts. They were the heartbeat of the bubble that made our planet habitable. The anomalies stacked. Solar particles born inside the heliosphere dropped to near zero. Galactic cosmic rays, once pushed back by the sun's breath, flowed in, not like a flood but like a tide no longer resisted. The magnetic field strengthened and steadied, but its direction didn't spin dramatically. That single fact kept the arguments alive. Was the heliopause a clean border or a set of laminated sheets, tangled by reconnection and draped in the interstellar field? While that was happening at the edge, IBEX's ribbon refused to behave. It brightened and dimmed with the solar cycle, as if responding to the sun's mood swings with a half-year delay. The ribbon's geometry pointed to a magnetic field outside, draped around our bubble like a taut fabric. Cassini's images supported it. Voyager's touch gave it weight. 3 very different instruments, one uneasy conclusion. The frontier wasn't empty. It was layered, structured, alive. Then came the day the plasma wave tone leapt. The pitch mapped to an electron density tens of times higher than the heliosphere's values. If you've never seen a room full of scientists listen, really listen to a graph, it looks like superstition. It is. The frequency is physics. Higher frequency meant more electrons. More electrons meant we pressed through to the very local interstellar medium. Not a guess, a measurement. But there was one problem, and it mattered. The temperature inferred from various models of that outside gas said hot, tens of thousands of degrees. Everything we were trained to feel about hot screamed danger. And yet Voyager showed no signs of roasting because in space, hot can mean very few particles moving very fast. Heat needs collisions. Out there, collisions are rare. The sensation of a furnace with no burn would haunt the rest of the story. In the aftermath, the word outside landed in headlines and phones rang. Inside, the conclusion was sharper and stranger. We'd breached a barrier that filtered radiation and sculpted a sky map from Earth. But the barrier wasn't a wall like a brick, more like a bruise, a region where two forces met and left a mark. The term stuck because bruises have edges you can press and feel, and that's what the instruments were doing, pressing. One detail buried in that first density spike would matter later. The exact pitch of the plasma wave, the way it climbed, told us not only that we were in denser stuff, but by how much. That number, electron density, would become our yardstick for every later storm, every echo, every map we drew of the boundary's thickness. The wall had a voice, and we'd finally learned how to hear it. To understand why the edge burns without burning us, we have to go back to the sun's breath. The sun's breath builds a bubble. To understand the bruise, start with the breath. The sun doesn't just shine, it blows. From every latitude, charged particles stream outward at hundreds of kilometers per second, dragging the sun's magnetic field with them. That outflow is the solar wind, and for most of the journey it's supersonic, faster than pressure waves can travel in the plasma. It races past Earth, past Jupiter's storms, and keeps going until it can't. Where it can't is called the termination shock. Think of a freeway that slams into a traffic jam. Upstream, cars fly. Downstream, they crawl and heat. The solar wind crosses that invisible shock and drops from supersonic to subsonic, turning kinetic energy into internal energy. Downstream of that, in the heliosphere, the wind is hot and turbulent, redirected tailward, trying to find a way around the competing pressure of the galaxy beyond. Every swirl, every eddy, is the sun negotiating with the interstellar medium. What nobody knew at the time Voyager launched was how alive that negotiation would be. Pressure isn't just one thing. There's thermal pressure from hot ions, ram pressure from the wind's bulk motion, and magnetic pressure from frozen-in fields. On the other side, the very local interstellar medium pushes back with its own particle pressure and a magnetic field that drapes around our bubble. Where those pressures balance, you get a contact discontinuity, the heliopause. It isn't a wall you can touch. It's a boundary that exists because forces agree to disagree there. Meanwhile, something else was happening that made the edge stranger. Neutral hydrogen from interstellar space slips across the heliopause because it's, well, neutral, uncharged and blind to magnetic fields. Inside the heliosphere, those neutrals swap electrons with hot ions in a process called charge exchange. You get energetic neutral atoms that fly off in straight lines and cold ions that can be picked up by the solar wind. Energy moves. Momentum moves. The boundary starts to glow in ENAs you can image from Earth orbit, which is exactly what IBEX did when it revealed that ribbon arcing across the sky. Here's where it gets personal. The first time I saw a simulation show the heliosphere inflating and deflating with the solar cycle, it looked like a heartbeat. During solar maximum, when the sun's magnetic field is tangled and eruptions are common, the wind's average pressure rises. The bubble swells, the heliosphere thickens, and the boundary is pushed outward. During solar minimum, the wind softens, the sheath thins, and the edge drifts inward. Not much by our standards, tens of astronomical units over years. But for a spacecraft like Voyager, that's the difference between silence and song. But there was one problem. Space outside isn't uniform. The interstellar medium looks smooth on a map, yet it's a patchwork of partially ionized clouds, ripples in magnetic tension, and density gradients that have their own histories. We're cruising through the local interstellar cloud, skirting structures tied to the local ribbon of cold clouds. As the sun moves, the interstellar field lines don't just sit there. They drape and twist, creating places where magnetic reconnection can bleed energy, where folds can create doorways, and where the solar wind's deflated croissant shape, or comet-like tail, depending on who you ask, decides how stresses distribute. While that was happening out there, back near the sun, the 11-year cycle quietly set the metronome. Flip the sun's magnetic polarity, and you change how its field threads the wind. That threading determines how cosmic rays are modulated as they try to work inward. It also sets the stage for how shocks from coronal mass ejections will pile into the heliosphere and ring the heliopause like a bell. Those are the very shocks whose echoes Voyager's plasma wave antennas would later turn into that rising tone. The heartbeat isn't just a metaphor, it's causality you can measure. So what shapes the bubble? Start with ram pressure, density times velocity squared of the solar wind. Let it crash into the total pressure of the VLISM, thermal, magnetic, and a trickle of cosmic rays. Add charge exchange, which siphons energy and seeds a population of pickup ions that act like a ballast. Stir in turbulence that cascades energy from big flows to small eddies, where it becomes heat. Then overlay the draped interstellar magnetic field, which adds tension like elastic bands around the bubble. Where this stew reaches stalemate, the heliopause forms. Get this? The balance isn't static and it's not symmetric. The sun's rotational equator is tilted relative to the galactic magnetic field. North and south lobes feel different stresses. Tail regions stretch or deflate depending on how tensions resolve. That's why the debate over comet tail versus croissant lobes isn't just an academic food fight. It's about where the bubble is strong and where it's thin. If you're plotting a human mission out of the ecliptic, this geometry isn't wallpaper, it's risk. Now remember that bruise metaphor. A bruise forms where pressure meets tissue and blood pools. Our boundary forms where pressure meets pressure and energy pools, some of it ending up as 50,000 K temperature that won't fry a hull because particle densities are too low to share that heat. That's the paradox we ran into at the end of the last act. The bubble's very existence makes that paradox inevitable. Accelerate a few particles a lot, and you can call it hot without ever feeling warmth. And yet this bubble is why life on Earth evolved under a certain radiation budget. Without it, the most damaging galactic cosmic rays would reach the inner system far more easily. With it, the sun's breath sets the baseline, thickening and thinning the shield over decades, shaping mutation rates subtly over eons. The bubble is our home's first line. It breathes with a star, flexes against a galaxy, and leaves a mark we can press with instruments and hear as song. Which raises the next question. If the edge is hot with almost no heat, where does that heat really come from? Where heat comes from when there's no fire. We called it hot, but not the kind of hot your skin understands. Temperature out there is a measure of how fast particles move, not how warm something feels. In a kitchen, heat leaps by collisions, billions of particles slamming into your hand every second. At the heliopause, the particles are so sparse you could fly a sheet of aluminum through and barely trade a whisper of energy. So yes, 50,000 Kelvin, but not a stove, not a flame. To get why, separate two ideas. One is kinetic temperature, average particle energy. The other is heat flux, how much energy moves per unit time. You can crank the first sky high and still starve the second if the density is low. Voyager didn't roast because there weren't enough electrons and ions to share their frenzy. Fewer billiard balls on the table means fewer collisions, even if each ball screams across the felt. So where does that kinetic frenzy come from? Start with charge exchange, the quiet saboteur at the boundary. Neutral hydrogen from the interstellar side drifts in, passes through magnetic curtains like they're not there, and swaps an electron with a hot solar wind ion. Suddenly, you have an energetic neutral atom, an ENA, carrying away momentum in a straight line, and a newborn cold ion sitting in the wind like a stone in a stream. The wind's fields grab that ion, spin it up, and bang, you've just moved ordered flow into random motion. That's heat. Pickup ions are the middlemen in this economy. They start as neutrals, get ionized by charge exchange or ultraviolet photons, and are picked up by the solar wind's magnetic field. They don't glide, they gyrate, forming ring distributions that feed turbulence. Turbulence is the cosmic blender. It takes big, organized motion and shreds it into smaller and smaller eddies until friction-like processes at tiny scales convert motion into thermal energy. No flame, just order dissolving into heat. Add shocks and things get spicier. Coronal mass ejections race outward and pile up in the heliosphere, steepening into shocks that press against the heliopause. When a shock crosses a gradient in density and magnetic field, it can reflect particles, accelerate them, and stir more turbulence. Some of that energy leaks across via reconnection, magnetic field lines from the sun and the galaxy snapping and rejoining, letting energy and particles trade neighborhoods. Each reconnection event is a small wire crossed in a vast circuit. Another way motion becomes hot. Now about that glow. The wall isn't a torch. It's neutral hydrogen energized enough to emit or to produce those ENAs that IBEX and Cassini imaged. ENAs are our messengers. Being neutral, they aren't herded by magnetic fields. They fly straight from the boundary to detectors near Earth, encoding where and how energy was deposited. IBEX's ribbon is essentially a bright return address stamped by regions where the draped interstellar magnetic field angles just right to reflect or generate ENAs efficiently. If the wall stores energy, ENAs tell us where the tabs go. Here's a whiteboard moment. A physicist I trust drew 3 arrows: turbulence, reconnection, shocks. Pick your poison, she said. All roads lead to heating. The fight in the literature is about proportions. Some models argue reconnection dominates, especially where the interstellar field presses hardest. Others stack the deck with turbulence fed by pickup ions. Still others show shocks doing the heavy lifting during solar max. The data say yes to all, but not equally, not everywhere, not always. That's why the ribbon brightens and dims with the cycle, why hotspots migrate, why Voyager hears a different tone after each storm. Language trips us too. Call it 50,000 K and people hear star, but stars are hot and dense. The heliopause is hot and thin. You need to camp there for a cosmic eternity to soak enough energy to raise a spacecraft's skin by a single degree. It's less furnace, more fever, a sign of stress, not a source that will burn you. That matters for headlines and for policy. Panic isn't useful, precision is. Meanwhile, the shape question lurks under the heating story. If the heliosphere is more croissant than comet, with twin lobes held by magnetic tension, then energy stacks unevenly. Lobes, folds, and polar cusps become natural places for reconnection and turbulence to pump up temperatures. ENA maps show anisotropies that fit this idea at some energies. At others, the old comet tail picture works. The truth may be nested, croissant-like near the flanks, tail-like far downstream. Heating will follow the scaffolding. And remember Voyager's metronome, the plasma wave tone. When solar storms push shocks outward, the tone shifts as those shocks ring the interstellar plasma. The pitch tells us electron density. The change in pitch over time tells us how quickly energy spreads and how thick the heated layers are. Match storm launch times at the sun with tone arrivals at Voyager, and you get a ruler, a way to measure the boundary's thickness and the speed at which heat percolates across layered shells. So the paradox resolves. No fire yet heat, no burn yet hot. The wall's temperature is the receipt for energy transfers at a contact boundary that never settles. It's the bruise we talked about, pressure meeting pressure, flow fighting field with charge exchange, pickup ions, turbulence and reconnection tallying the blows. And if it can glow in ENAs and sing in plasma tones, we should ask the obvious next question. Who drew the first sky map that proved the glow was real? The sky map that shouldn't exist. We asked who saw the glow first. The answer came from a satellite that never left Earth's gravity. IBEX didn't point a camera, it opened a mailbox. Energetic neutral atoms left the heliopause and flew straight in, untouched by magnetic fields, each one a stamped letter from the edge. After 6 months of collecting and turning, the first all-sky map came together, And there it was, a narrow, bright arc, a ribbon wrapping across the sky where no model put anything. Stakes landed fast. If that ribbon was a mirage, then our boundary physics was wishful thinking. If it was real, we were looking at a fence, a swath of space where energy preferred to go, where particles turned around, where the interstellar magnetic field draped in a way that picked out a single great circle. You don't get a structure like that by accident. It meant order. It meant the galaxy's field was steering the conversation. Action first. IBEX maps showed an excess of ENAs at specific energies, peaking where the line of sight made the interstellar magnetic field perpendicular. That geometry screamed resonance, conditions that reflected or generated ENAs efficiently. The ribbon shifted brightness with the solar cycle, not instantly but with delays that matched the time it took solar wind changes to propagate to the wall and for ENAs to make the return trip. The signal pulsed with the sun's heartbeat, yet it was stitched to the galaxy's field. 2 metronomes, 1 melody. Meanwhile, Cassini's Inca instrument, out by Saturn, saw a complementary glow at higher energies, painting a broader, fatter edge around the heliosphere. 2 very different detectors, 2 vantage points, same implication. The boundary wasn't a fuzzy smear. It had texture, ridges, folds, a highlighted curve. And far away, Voyager's in situ whispers. The cosmic ray tide, the magnetic firmness, the plasma wave tones, gave the maps a touch point. We could overlay sound on sight and the fit wasn't perfect, but it was close enough to change minds. Here's the human moment. At a briefing, someone said ribbon, and it sounded gentle, decorative. Then the plots hit the screen, a spear of brightness slicing the sphere of the sky. A communicator in the back muttered, "That's not a ribbon, that's a wall," and the word stuck. It wasn't precise, but it caught what people felt looking at the map, that sense of a boundary asserting itself. Impact ripple. The old picture of a neat comet-like bubble trailing a long tail didn't vanish, but it had to share the stage. The ribbon's alignment with the interstellar magnetic field suggested magnetic tension was doing more heavy lifting than gas pressure alone. Models that bent the heliosphere into 2 lobes, what would later be nicknamed the deflated croissant, started matching parts of the ENA pattern better than a single, smooth tail. At some energies and latitudes, the croissant fit. At others, a tail returned. The shape wasn't one thing, it depended on how and where you looked. But there was one problem, and it wouldn't go away. The ribbon moved. Over 11 years of IBEX, its brightness waxed and waned and its position nudged, tracking changes in the solar wind and the sun's field with a lag. If this was a fence, it wasn't nailed down. It breathed. Energy bands didn't play by a single rule either. Higher energy ENAs traced broader regions. Lower energy ones hugged the ribbon tighter. Any model that tried to lock the heliosphere into a single geometry collapsed under those shifts. While that was happening in data rooms, Voyager's team used the maps as context, not gospel. You don't steer by a mural, but the mural told you where the freeway bent and where traffic piled up. When Voyager heard a new plasma tone months after a strong solar eruption, IBEX brightened not long after in the same sectors, as if the wall had swallowed a shove, heated, and radiated a flood of neutrals back at us. The timing lined up well enough to make it a habit. Check the sun, check Voyager's ears, check IBEX's sky. Here, S where the croissant vs comet fight turned practical. If magnetic tension pinched the flanks into lobes, those lobes could host folds and cusps, places where field lines converged, where reconnection could pump heat and open temporary doors. The ribbon's persistence along one great circle could be the signature of that draping, a kind of magnetic highway where particles found the same angles over and over. Yet Cassini's wider glow hinted at a sheath that still swept tailward like a comet. The compromise picture got messy but useful. A croissant-shaped nose and flanks feeding a more traditional tail downstream. Complication piled on. The ribbon wasn't just moving, its spectral slope, how brightness changed with energy, refused to sit still. During solar maximum, some sectors flattened, consistent with stronger shocks and more pickup ion turbulence feeding ENA production. During minimum, the ribbon sharpened, as if quieter conditions let magnetic geometry dominate. No single heating mechanism could win everywhere. You had to juggle turbulence, reconnection, and shocks on a schedule the sun wrote and the galaxy enforced. Impact again. With IBEX and Inca, we had a weather map of the wall. Not perfect, not instant, but good enough to watch the fence flex. That mattered for everything from predicting cosmic ray backgrounds to picking trajectories for probes that might want to thread between hot zones. It also reframed Voyager's story. We weren't just listening to a boundary. We were seeing it choose paths for energy, lighting up where the invisible field told it to. Then came a cliffhanger worthy of headlines. Voyager crossed the line many thought would end the debate. The plasma wave tone leapt, the cosmic rays rose, the solar particles vanished. By the numbers, we were outside. But the maps kept shifting, and the magnetic field direction near Voyager didn't pivot as cleanly as a modeler's sketch. The wall, it turned out, could be crossed and still reach back. The story wasn't over.